right, we are on the last page of the Unit 4.1 packet, which is where we're going to finally look at transition metals. We've said that transition metals are a little bit different than other metals. We haven't been able to predict their charge, and therefore we haven't done anything with transition metals this whole unit. Some names that we're going to see for ionic compounds have Roman numerals in the middle of the name, and you see examples of that down below. So some compounds might be something like vanadium 3 chloride or lead 4 oxide. And so why do we have those Roman numerals? When do we need them, and what do they mean? So transition metals, remember that transition metals are this section, the D block of the periodic table. Transition metals can form more than one ion. They can form more than one charge. That's why we haven't been able to predict the charge of transition metals up to this point, because they have the ability to make more than one different charge. We are going to use a Roman numeral in the name to state the charge of the metal in the compound. So this is really important. The Roman numeral tells us the charge. So if I say lead 2 chloride, the 2 means lead with a charge of 2, because otherwise, if I don't tell you, you don't know what the charge of lead is from the periodic table. So you have to be told in the name what the charge is. In addition to the transition metals, there are 2 other metals, which are lead and tin, that also can form more than one ion and also need Roman numerals in the name. Okay. So those 2 elements, lead and tin, are right here. And the reason why these need Roman numerals as well is because they were in this question mark category. They were in the group that we didn't know the charge of. This was that column that we said could go backwards for or forwards for to become like a noble gas. It wasn't sure what to do, and we just skipped it. So these 2 metals would need a charge specified in their name. There are a couple of transition metals, just as a note here, that don't have Roman numerals, so you might come across those. So I'm just going to highlight all the ones that would need Roman numerals on here. And there are 3 that don't. There are 3 transition metals that only ever form one charge, and that's zinc, silver, and cadmium. So these 3 technically don't need Roman numerals in their name. And they're actually just on your reference sheet in common cations. Silver always makes a +1. Cadmium and zinc always make a +2. So those are actually listed on your reference sheet. Those are the only charges those 3 elements make. And so technically those 3 elements actually don't need Roman numerals in their name, even though they're transition metals, because they only make more than one, or they only make one charge, not more than one. All right, so let's go ahead and take a look at this. And I'm going to do this a little bit backwards. I'm going to skip to the bottom of the page. So let's go ahead and practice what happens if we're given the name. How do we turn that into a formula? So remember that anytime we're given a name, we need to figure out what is the positive, the cation, what is the negative, the anion, and then are they a perfect match or a crisscross? So vanadium is the element V. It's a transition metal. So if I look on the periodic table to figure out its charge, I would say no idea. It's in the section that I don't have a charge for. But luckily the name tells me the charge. Vanadium has a charge of 3. The Roman numerals are only ever used for metals. Metals are always positive. So the charge for the Roman numeral is always going to be positive, that number. Chloride is from the element chlorine, and the element chlorine has a charge of -1. Okay, once we look at that, we look and see, are they a perfect match or a crisscross? And in this case, we're going to need to crisscross. So vanadium, I need 1, so just V. And then chlorine, I need 3, so VCl3. Next up, lead. Lead is Pb. IV is the Roman numeral for 4. So this is lead with a charge of 4. Just going to go ahead and add my Roman numerals on here. I is 1. II is 2, III is 3, and then IV means 4, V means 5, and VI means 6. 1, 2, and 3 are pretty self-explanatory. If you know that 5 is V, then IV and VI, it's really just the idea that we're one above and one below 5. So I always kind of think is VI means 5 and 1, which would get us to 6. And that means IV is 1 less than 5, which would get us to 4. All right, so once we have that, we have lead, 4, and then oxide is oxygen. Oxygen has a charge of -2. And this is not a perfect match, so we're going to crisscross. And that would get us Pb with a 2 next to it. And then oxygen would have a 4 next to it. Just as a note, this is actually incorrect. So I'm going to go ahead and cross it off on here. The problem with this is that we said before that ionic compounds should be the smallest whole number ratios. So for something like sodium chloride, they're a perfect match, NaCl. I don't write Na10Cl10. So when I look at this, I see Pb2O4. 2 and 4 is not the smallest whole number ratio. Both of these numbers could be divided by 2 to make them smaller. And that's what we actually want to do. So lead, Pb, if I take 2 and divide it by 2, I just need 1 lead. And then oxygen, 4 divided by 2 would be 2. And so what this formula says is for every 1 lead, I need 2 oxygens. So yes, if I have 2 leads, then I need 4 oxygens, but this is our smallest whole number ratio. All right, so continuing on here, iron, Fe, +2. Oxide we just had, that's a -2. +2, -2 is a perfect match. So I just take the 2 symbols, Fe and O, and stick them together. Next up is nickel with chlorine. So I'm going to have you pause here, figure out our 2 charges, see if they're a perfect match or a crisscross, and then try the next 2. Once you've tried it, hit play again, and go ahead and check the rest of your answers. All right, hopefully you tried these on your own now. So nickel's a +2, chlorine's a -1. Those are going to be a crisscross. So I need 1 nickel and 2 chlorines. Copper is a +1. Sulfate, as soon as you see this ATE, that tells you it's not an element. That's a polyatomic ion, which is on the back of our reference sheet. So sulfate is SO4 with a charge of -2. That's going to be a crisscross. So copper is going to have a 2 next to it, and then sulfate, just 1. If it was anything besides 1, I'd need to put parentheses around the polyatomic before I crisscrossed. Nickel, +2, and then carbonate. We look on here for carbonate, CO3 with a charge of -2. Okay. +2, -2 are a perfect match. So I'm just going to go ahead and push those 2 symbols together, Ni, and then CO3. Okay. Notice that I'm not getting rid of the 3. That's part of carbonate. If I just wrote CO, that wouldn't be carbonate anymore. For it to be carbonate, it has to have the 3 on it. All right, so that's writing formulas from names. If we wanted to go the other direction, looking at a formula and writing the name, we are going to have to figure out what the charge is. So just as an example, what is the name of Mn3p4? So I'm actually going to kind of skip down to the bottom where it says name the compound. Mn is manganese. So that's an element on the periodic table. And because it's a transition metal, I don't know the charge, so I'm going to have to write the charge as part of the name. So I'm going to leave space here for it. And then I'm going to name the second part. P is phosphorus. Remember that we need to change the ending to "ide." So instead of saying phosphorus, I'm going to say phosphide. I'm almost done with the name. The only thing I have left is I need to figure out the charge. So what is the charge of manganese here so that this overall compound has a charge of 0? What I typically do for this is I draw a picture. So Mn, there's 3 of them. It says Mn3, so I'm going to write Mn 3 times. And then phosphorus, there's 4 of them, so I'm going to write phosphorus 4 times. I know that overall, this compound has a charge of 0. A compound is always neutral overall, there's no charge on it. So if I know the charge of phosphorus, phosphorus has a charge of -3. So this is -3, and that's -3, and this is -3, and this is -3. The total here, 3, 6, 9, 12, is -12. And in order to get to 0, that must mean that all of the manganeses must be +12, so that +12 and -12 equals out to 0. Well, what I really want to know is, well, what's the charge on a single manganese? Not the charge on all of them combined, but just the charge on a single manganese in this compound. If I know that there's 3 of them and they have to equal to 12, 12 divided by 3 would give me this number that's going to go here. So 12 divided by 3 would be +4. So in this case, I know that manganese is going to have a charge of 4 in the compound. And I could double check that. If I know manganese is a +4, and phosphorus is a -3, those are not a perfect match. That would be a crisscross. And my formula then would be Mn3P4. And if I check what we started with, that's the same formula. So that tells me that I did this correctly. Okay. So we looked at the total charge of all the phosphorus. We said that was -12. That means that all the manganeses needed to be +12. And since there were 3 of them, we did 12 divided by 3 to get +4. Some people will notice that the other way that we could have done this is taken our formula and uncrisscrossed it. So if we would have uncrisscrossed it, we would have seen that manganese had a charge of 4 before it was crisscrossed. That works sometimes, but it doesn't work if the formula was reduced. Like we saw down here, if we uncrisscrossed this one for lead, 2 would have been on Pb, but lead was actually a +4 because we had to reduce our formula from Pb2O4 to PbO2. So if we ever changed our formula to make it the smallest whole number ratio, then uncrisscrossing doesn't work. So be careful with that. If that's something that you notice and you want to try, that's fine, but you just want to make sure that when you're getting your final answer, you're looking at the charge that you're assigning to both elements and saying like, oh, if I uncrisscrossed here, that example at the bottom, oxygen would have been a -1, but that's not the charge of oxygen. So be careful with that method. Okay. All right, let's take a look at our next one. Au is gold, which again is a transition metal. We're going to need a Roman numeral. And then nitrogen, which we change the ending to "ide", so gold nitride. Next would be nickel oxide. Sn is tin oxide. Iron nitride or nitrogen. Cr is chromium. P is phosphide. And then our last one on here, this one's a little bit funky because I actually see 3 different elements, which tells me that something is on the polyatomic list. So if I look at this, TiNO3, so there's no TIs on here at all, but I do see NO3 is called nitrate. So this whole NO3 chunk is called nitrate. Ti is titanium. All right, so from here, we can go ahead and try to figure out the charges. So if we look at our first example, we have 3 Aus and we have nitrogen. So if I look at nitrogen, nitrogen has a charge of -3. And so if I want this whole thing to be 0, I have -3 so far. So I need my 3 golds to end up being +3 total, so that +3 and -3 is 0. Well, what's the charge on each gold then? +3 divided into 3 different pieces would be +1 for each of them. So if this is gold with a charge of +1, this is gold 1 nitride. All right, next up, nickel oxide. I have 2 nickels. We have 3 oxygens. Each oxygen has a charge of -2. So this right here is a total of -2, 4, 6 total, which tells me that my 2 nickels must be +6 total, so that the answer is going to end up being 0 for the whole compound. So the charge on each nickel, if the total is 6 and there's 2 nickels, that's +3 for each nickel to get us to a total of 6. Again, if you wanted to try to uncrisscross, you could. And so if you uncrisscrossed this, you would see that the 2 must have been on the oxygen before, and the 3 must have been on the nickel before, and that's actually what we have here. If you want to try to use this method, you just need to check the other element and make sure, is oxygen actually a -2? Yes, it is. Then that tells you that your uncrisscrossing method worked. Okay. For number 3, we have tin oxide. So we have 1 tin and 2 oxygens. We just set up here oxygen's a -2. So that gives us -4 so far. And we know that the whole compound should equal 0. So this one needs to be +4, and there's just 1 tin. So our tin here must be a charge of 4. If we wanted to try to uncrisscross this one, we would have taken the 2 and put it up on the tin. The tin had no number down low, which means a 1. We would have put that up here. And if you look at this, oxygen with a charge of -1, oh, that's incorrect. Oxygen doesn't have a charge of -1. And that would tell you that in this case, uncrisscrossing didn't work. The oxygen was wrong. So that means the tin here that I just wrote the charge for is wrong too. So you can't uncrisscross for everything. But if you want to try that method, you can, and just double check, and look at the other element. Is it correct or not? If it's correct, then the uncrisscrossing worked and you can use it. Okay. All right, this one is a perfect match. Fe and N, right? 1 iron and 1 nitrogen. What that tells me is whatever the charge is on nitrogen, it's the same as the charge on iron. So nitrogen has a charge of -3. So iron is going to be positive, but the same number. So it's going to be +3 since they're a perfect match. All right, our next one we have chromium, and that's making a bond with 2 phosphorus atoms. Phosphorus has a charge of -3. So this one's -3 and this one's -3, which means that total we have -6. In order to get to 0, -6 must have a +6 to balance it out. And there's only 1 chromium. So if there's only 1 chromium, then the chromium has a charge of 6. Our last one on here is a little bit tricky. We have titanium, and then I put the NO3 in parentheses because that whole thing was called nitrate. And so that entire chunk, nitrate, NO3 is a whole chunk. The 3 wasn't crisscrossed, it's just part of nitrate. The charge on nitrate is -1. So when I look at this, here's the charge on the nitrate, and my formula tells me that there's 1 titanium and there's 1 nitrate. This is actually a perfect match. So if the nitrate is -1, then the titanium must be +1, titanium 1 nitrate, since they're a perfect match for each other. All right, this can be a little bit tricky at the beginning, so you just got to practice these. But again, that Roman numeral is going to tell us the charge of the transition metal, and we use that to write the formulas. And when we write names, we have to include the transition metal charge in the name as a Roman numeral.